All right, guys, in this lesson, we're going to be looking at chi-squared tests for goodness of fit. So our objective here is to state the hypotheses and expected counts for chi-squared tests. We will also want to calculate the test statistic, degrees of freedom, and p-value for a chi-squared goodness of fit test, as well as perform a chi-squared test for goodness of fit. So, very similar to the tests that we have been looking at in the last couple chapters, you're going to have to perform the four-step process again to fully solve for this, but there are a few parts that differ as far as kind of what we're looking at, or the problem itself differs as well. So let's just kind of get a feel for what this is. So in this example, Mars Incorporated, which is headquartered in McLean, Virginia, makes milk chocolate candies. Here's what the company's Consumer Affairs Department says about the color distribution of its M&M's milk chocolate candies. So on average, M&M's milk chocolate candies will contain 13% each of browns and reds, 14% of yellow candies, 16% of green candies, and 20% of oranges, and 24% of blue candies. And so our goal here is to kind of perform a chi-squared test based off of this. So in this example, Jerome's class did the Candyman can activity. The one-way table below summarizes the data from the class's sample of M&M's milk chocolate candies. In general, one-way tables display the distribution of a single categorical variable for the individuals in the sample. So even though we're supposed to get 13% each of brown and red candies, 14% of yellow candies, 16% of green candies, 20% of oranges, and 24% of blues, the class, or Jerome, actually got 9 blue candies, 8 orange candies, 12 green candies, 15 yellow candies, 10 red candies, and 6 brown candies for a total sample of 60 candies in this case. So essentially, this leads to what is a chi-square goodness of fit. And that is essentially how well does our sampling distribution, or how well does this distribution match up with the known population distribution, or what it's actually supposed to come out to in this case, if we're given that kind of proportion here. And so when we would be stating hypotheses in this case, since we know that there's supposed to be about 24% blue candies, and Jerome is interested if his proportion is wrong, then we would state a hypothesis like so, where our proportion is actually equal to 24%, or our alternate hypothesis would be our proportion does not equal 24%, which in this case it's kind of seeming that way because 9 is certainly not the largest number on here, and 24% is the largest percentage of any of the colored candies. So you would think that we would have more blues than we would any other color in here, but that just wasn't the case. So we're essentially trying to find the difference between what the population distribution is and what the sampling distribution is in this case. So since we know the expected proportion of candies and have a fixed sample size at 60, how many blues were we supposed to get? Well, because our proportion was 24% and we had a sample size of 60, we would just take 60 times 0.24, and that gives us an expected count of 14.4. We were expected to have 12 orange candies based on their proportion of 20%, and so on and so forth. So we were expected to have 9.6 green candies, 8.4 yellow candies, 7.8 red candies, and 7.8 brown candies. So this essentially was our expected count of candies based on the proportion that the company actually gives from that. So if we were wanting to find our chi-squared test statistic, so since we were expecting 14.4 and we only got 9 blue candies, is that a significant difference? So our chi-squared statistic would be finding the observed minus the expected values squared divided by the expected values. And this essentially is how far the observed counts are from the expected values. And again, chi-squared is labeled as kind of this squiggly x squared in that case. So that's its notation. So if we were going to find the chi-squared statistic for this particular example right here, what we would do is we would take our observed values right up here from the actual sample itself and pair them up with our expected values. And so we would take 9 minus 14.4, square that, and divide it by 14.4, plus 8 minus 12 squared divided by 12, plus 12 minus 9.6 squared divided by 9.6, plus 15 minus 8.4 squared divided by 8.4, plus 10 minus 7.8 squared divided by 7.8, plus 6 minus 7.8 squared divided by 7.8. And so if we were to add all of those values up, we would get a chi-squared value of 10.18 in this case. So what do these chi-squared distributions really look like? Well, this is a lot of what they look like. And if you were to look up a chi-squared distribution table, that's essentially what you would get, is you would get a lot of these nasty looking curves that all differ essentially based on their degrees of freedom. So the chi-squared distributions are a family of density curves that take only non-negative values and are skewed to the right. A particular chi-squared distribution is specified by giving its degrees of freedom. The chi-squared test for goodness of fit uses the chi-squared distribution with degrees of freedom that equal the number of categories minus 1. So again, right now we're about to get into kind of what all this curve really means, but it's important to note that these curves are going to adjust based on the degrees of freedom, and we find the degrees of freedom by taking the total number of categories minus 1. So in this case, we have 1, 2, 3, 4, 5, 6. We have 6 total colors that we can get, and those colors represent our categories, essentially. And so because we have 6 total colors, our degrees of freedom would be 5, because we just take 6 minus 1, that gives us a degrees of freedom of 5. And so our curve, they don't show it here, but our curve is going to look something kind of close to this. Degrees of freedom is equal to 4. So we use that curve to kind of find our p-value in this case. And so in the last example, we computed the chi-square statistic for a random sample of 60 M&Ms, milk chocolate candies, in Jerome's class. And that gave us a chi-squared value of 10.180. Now let's find the p-value based on that chi-squared value. So again, this is kind of like your test statistic or your z statistic or t statistic, like in significance tests, but we're using chi-squared instead of that statistic to find p. So because all of the expected counts are at least 5, and I'm about to get into what that actually means, the chi-squared statistic will be modeled well by a chi-squared distribution when our null hypothesis is true. There are 6 color categories for our M&Ms, milk chocolate candies, so our degrees of freedom again is 5. 6 categories minus 1 equals 5. The p-value is the probability of getting a value of chi-squared as large or larger than 10.180 when our null hypothesis is true. So again, this curve represents the chi-squared curve with the degrees of freedom at 5. And essentially what we're trying to find when we're looking at the p-value is the area under the curve when it is a little greater than 10 right here. So we're trying, this whole blue shaded area right there represents the p-value, or the probability that we are going to get a chi-squared value as large or larger than that number when our null hypothesis is true. And again, this figure just shows the probability as an area under the chi-squared density curve with the degrees of freedom at 0. So that's essentially kind of a visual representation of how we find that p-value. Now, this is kind of a little more complicated way of finding both the chi-squared value and the p-value, but essentially what we could do is we could take the observed values right here and enter them into L1. Then we could take the expected values from our table and enter them into L2. And then for L3, what we could do is we could take L1 minus L2 squared and divide it by L2. And that would give us all of these numbers, and then from that we could just take the sum of every number that we get in L3, and that would give us our chi-squared value of 10.18. Then if we wanted to find the p-value, what we could do is we could go to second vars and find our chi-squared CDF, and because we are trying to find the probability that it is as large or larger than 10.180, we would enter in 10.180 for our lower bound, a really high number for our upper bound with our degrees of freedom at 5, hit paste, and that would give us our p-value of 0.0702 or 3. However, there is a much simpler way to find that in the calculator that I will get into in just a second. Now, because this is a test, there are conditions that must be met in order for our test to be fairly valid in this case. So the first condition that must be met is that it must be random. The data comes from a well-designed random sample or randomized experiment. It must be independent. So when sampling without replacement, we want to check that the number in our sample has to be less than 10% of the total population that it represents. And then instead of normal, we must pass a large counts condition. So all expected counts are at least 5 in this case. And now normally with every other test we've done so far, our counts must be at least 10 or greater than 10. In this case, they have to be at least 5. And we're not necessarily checking for a normal sampling distribution. We are just checking to make sure that the counts are large enough so that the math will actually work. However, you want to make sure that you are not basing this value off of the observed values. In other words, you might want to call this an expected counts condition and not a large counts condition, because we are basing this off of the expected counts condition. So what I mean by that is that if I were to go back to this table right here, I have to make sure that every single expected value right here is greater than or equal to 5. It has to be at least 5, not the observed values. The observed values can be lower than that if they need to be, but the expected values must be greater than or equal to 5 in this case. So those are the 3 conditions that must be met. So now let's kind of get into the test itself, or making sure that we meet all the requirements for this test. So suppose that the conditions are met. To determine whether a categorical variable has a specified distribution in the population of interest expressed as the proportion of individuals falling into each possible category, perform a test of our null hypothesis, which is the stated distribution of the categorical variable in the population of interest is correct, and our alternative hypothesis, which is that the stated distribution of the categorical variable in the population of interest is not correct. So our null hypothesis and our alternate hypothesis are going to look a little different for these chi-squared tests, basically. They're not going to be quite as simple or easy to comprehend as they have been for significance tests. They are going to be a little more wordy in this case. So first we want to start by finding the expected count for each category, assuming that our null hypothesis is true, then calculate the chi-squared statistic. And so again, we want to make sure that we calculate the chi-squared statistic as well as our p-value, which is the area to the right of the chi-squared under the density curve of the chi-squared distribution with k-1 degrees of freedom in this case. So let's go ahead and look at an example of how we would actually solve this test, basically. So in his book, Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it to the highest level of the game, specifically because January 1 is the cutoff date for youth leagues in Canada, where many National Hockey League players come from. Players born in January will be competing against players up to 12 months younger. The older players tend to be bigger, stronger, and more coordinated, and hence get more playing time, more coaching, and have a better chance of being successful. To see if birth date is related to success, judged by whether a player makes it into the NHL, a random sample of 80 NHL players from a recent season was selected and their birthdays were recorded. The one-way table below summarizes the data on birthdays for these 80 players. So essentially what they did was they took 80 players and 80 NHL players, and they tried to see when their birthday actually was, to see if January birthdays had more of an effect on these young men becoming players that would compete in the NHL. So we noticed that there are 32 players with birthdays between January and March, 20 players with April to June birthdays, 16 with July to September, and 12 to October to December. So we want to determine, do these data provide convincing evidence that the birthdays of NHL players are not uniformly distributed throughout the year? So that's kind of where we get our null and alternate hypothesis, is do these provide convincing evidence that the birthdays of NHL players are not uniformly distributed throughout the year? So I'm going to come back to that slide in just a second. First, we want to, again, state our problem. So we want to define the parameter, which is the distribution of their birthdays of all NHL hockey players' birthdays in the 4 quarters of the year. Okay, from there, we want to define our hypotheses, which is our null hypothesis is that there is no difference in the proportions of birthdays, essentially. They are all equal to one another. Our alternate hypothesis is that at least one proportion will be different in this case. And so, again, the null and alternate hypothesis are a little more wordy, and you don't have to state your null hypothesis like this. This may be a little more complicated to understand. You could just simply say in words that the proportions of birthdays in the 4 quarters of the year are no different, basically. And that would be completely fine for your null hypothesis. Okay. From there, we want to plan, or we want to check to make sure that our 3 conditions are met. So we are told that the sample is random. 80 is going to be way less than 10% of all NHL players. And since all expected counts are 20 in this case, so we have 80 players divided by 4 quarters in a year, so we should expect that 20 players would be born in each one of the 4 quarters of the year, which again represents our null hypothesis right here. Since all of those are greater than 5, the expected counts condition is met, or the large counts condition is met, and 20 is going to be greater than 5 in this case. From there, we would perform our do portion, which is that we will run a chi-squared test for a goodness of fit. And again, if we run our chi-squared like that, we should get a value of 11.2 with a p-value of 0.0107. Now, how you do that? If you go to stat edit right here, and let's say that I want to enter in all of my observed values, all the values that I get from this table right here in for L1, and then all of my expected values of 20, basically, for all 4 quarters of the year. And for L2, what I can do is I can then hit stat again, arrow over to tests, scroll up so that you get to the bottom of the list, and then keep scrolling up until you see D right there, which is the chi-squared GOF test. Then you want to make sure that L1 is your list for observed, L2 is your expected values list with the degrees of freedom of 3, because again we have 4 total categories, so we take 4 minus 1, that gives us 3. From there, hit calculate, and that should give you your chi-squared statistic right there, as well as your p-value right there. And then if you wanted to graph it, you could graph it as well based off of that. So that gives us our chi-squared test for goodness of fit. And since, if we were comparing that to a significance level of 0.05, since our p-value of 0.0107 is less than 0.05, we would reject the null hypothesis, as there is convincing evidence that the distribution of birthdays in the NHL are not evenly distributed throughout the year.